Hello, welcome back to Sleep Science. Wherever you are right now, whatever the room sounds like, whatever time it is, look around you. If there is any light in the room, notice it. In 1 trillion years, there will be no light left anywhere in the universe. Not one star, not one galaxy, not one photon. Tonight, we take the longest journey science can imagine, to the very end of everything. Right now, as you lie there, the universe is in its golden age. Stars forming, galaxies spinning, light in every direction. But this era has an expiration date. Not soon, not even close to soon, but the clock is running. And tonight we are going to follow it all the way to zero. Let's start here, with right now, with this moment that you are in. Right now, the room around you is warm. The air is breathable. Somewhere outside, the sun is either shining or it has set, but it will rise again tomorrow. That sun will burn for another 5 billion years. 5 billion years of tomorrows. And that is just the beginning of the story we are telling tonight. The universe, as best we can measure it, is about 13.8 billion years old, which sounds ancient, and by any human measure, it absolutely is. Civilizations have risen and collapsed. Mountains have grown from nothing and been ground back to sand. Species have appeared and vanished. And all of that, every dynasty, every ice age, every extinction event, every moment of evolutionary change, all of it fits inside a span of time that is, cosmically speaking, fairly recent. We are not even teenagers yet. The universe is in its infancy still. Think about what that means. The stars you can see on a clear night, most of them are young, some of them are old, but even the oldest stars burning right now formed in a universe that was already billions of years old, and they are burning still. There is so much fuel left, so much hydrogen still waiting to be fused into helium in the cores of stars scattered across hundreds of billions of galaxies. This era, the stelliferous era, scientists call it, from the Latin word for stars, is defined by light, not metaphorical light, real physical light, photons streaming in every direction from trillions of stellar furnaces, spread across a cosmos that stretches in every direction further than any number feels real. The stelliferous era is what we live in. It is what we have always lived in. Every human who has ever existed has opened their eyes into this era of light, looked up and seen stars. That is so easy to take for granted that it barely registers as remarkable. But it is remarkable. It is genuinely, deeply remarkable, because it will not last forever, because there is a version of the universe where none of this exists. A version where the cosmos is cold and dark and silent and utterly without process. And that version is not some strange, hypothetical nightmare. It is the future. It is where all of this is going slowly, with the patience of something that does not need to hurry, because it has all the time there is. We are right now in the single most interesting era the universe will ever produce. Let that sit for just a moment. Stars, light, galaxies, planets, oceans, atmosphere, life. The ability to lie in a warm room and breathe and think and wonder. All of this is a feature of this era. The stellar era. The bright burning epoch that began a few 100 million years after the Big Bang and will continue for trillions of years to come, but will not continue forever. You exist in this era. That is not nothing. Now, we are not in the early part of the stelliferous era anymore. That is worth saying clearly. The first generation of stars, the population 3 stars, the ancient massive furnaces made almost entirely of hydrogen and helium with barely a trace of anything else. Those are all long gone. They burned hot and fast and died in catastrophic explosions billions of years ago, seeding the universe with heavier elements. Carbon, oxygen, iron, the raw ingredients for planets and eventually for life. Every atom of calcium in your bones, every atom of oxygen in your lungs, every atom of iron in your blood. That material was forged in the cores of ancient stars that ended their lives before the Earth existed, before the solar system existed, before our galaxy looked anything like it does today. You are made of star stuff. not metaphorically, literally. The atoms in your body were synthesized in stellar cores, expelled in stellar deaths, gathered by gravity over billions of years into gas clouds, compressed again into new stars and the planets orbiting them, cycled through geology and chemistry and eventually into biology and eventually into you lying here tonight, which is strange to hold in your mind. You are a temporary arrangement of atoms that the universe has been building toward for billions of years, and you are lying in a warm room during the Golden Age, the bright era, the era when all of this is possible. There is a kind of peace in understanding where you are in the story, and tonight we are going to follow the story forward. Not because the future is frightening, it is not. If anything, the sheer distance of what comes next is the most reassuring thing science has ever given us. But because the story itself is extraordinary, because the universe has a plot in a sense, a genuine arc that moves from light to darkness to a silence so complete and so final and so far away that the distance between now and then is itself one of the most beautiful facts in all of science. The stelliferous era, we live in it, and we should appreciate it. Stars are forming right now. Right now, this second in nebulae, spread across every galaxy in the observable universe, gas clouds are collapsing under their own gravity. Clumps of gas are pulling themselves together, compressing, heating, until the pressure and temperature at the core become so extreme that hydrogen nuclei begin to fuse. Protons smashing into protons, releasing energy. That energy, that flood of radiation pushing outward from the core, is what we call a star, a new sun, a new furnace in the dark. This is happening in thousands of galaxies simultaneously. Millions of new stars coming to life in this instant, this very second, as you lie here breathing. At the same time, stars are dying, more quietly for the most part, at least the ones that are not massive enough for dramatic endings. A medium-sized star, something like our Sun, burns through its hydrogen over the course of about 10 billion years. The Sun is roughly halfway through its life. When it exhausts the hydrogen in its core, it will expand into a red giant swallowing Mercury and Venus and possibly Earth. And then it will shed its outer layers in a beautiful expanding shell of gas called a planetary nebula. And the core will remain as a white dwarf, an incredibly dense, incredibly hot, slowly cooling remnant. No more fusion, no more new energy, just slowly releasing heat into the void over billions of years. That is the standard death, the ordinary ending. For most stars in most galaxies, that is how it goes. And right now, all of that is happening everywhere simultaneously. Stars being born, stars living through their Middle Ages, stars in their red giant phase, stars dying as white dwarfs, stars dying as neutron stars after more violent deaths. Somewhere out there, right now, a supernova is detonating. A massive star collapsing and exploding in a burst of energy so extreme that for a few seconds it outshines its entire host galaxy. The universe is busy, and this busyness, this constant cycling of matter through stellar furnaces and back out again, is what characterizes the era we live in. It is a physical process, gravity pulling gas together, fusion releasing energy, radiation pushing outward, gravity winning again eventually. A constant back and forth that produces light, that produces elements, that produces the raw ingredients for everything we have ever known. But here is the thing about the stelliferous era. It has an end. The universe began with a finite amount of hydrogen. Most of the universe's mass is dark matter, which does not participate in stellar processes. The ordinary matter, the baryonic matter, the stuff that can form atoms and molecules and stars and planets and people, that is only about 5% of the universe's total energy content. And of that 5%, a significant portion has already been cycled through stellar processes. Hydrogen has been fused into helium, helium into carbon and oxygen, heavier elements forged. Some of that material is locked up in dead stellar remnants. Some of it is in planets. Some of it is in you. Every fusion reaction is a one-way door. Hydrogen goes in, helium comes out. The helium can fuse into heavier elements under the right conditions, but you cannot get your hydrogen back. The fuel is being spent, slowly, over timescales so vast they are nearly impossible to feel as real, but it is being spent. And when the last of the available hydrogen is exhausted, when the last cloud of gas has either collapsed into a star or been blown away by stellar winds or otherwise used up, there will be no more new stars. The assembly line stops, and from that point on, the universe can only get darker as the existing stars burn through the remaining fuel and go out, one by one, over the course of hundreds of trillions of years. 100 trillion years. That is the approximate lifespan of the stelliferous era. 100 trillion years from the Big Bang to the last star going out. We are currently about 13.8 billion years in, which means we are not even 1/15,000th of the way through the era we are living in. 1/15,000th. If the stelliferous era were a single day, we would be at 0.006 seconds past midnight. We are at the very beginning. And even that word, beginning, barely captures it, because the beginning is not just where we are in terms of time. It is where we are in terms of complexity and richness and activity. The early universe was simpler, pure hydrogen and helium and dark matter and radiation. The universe a few billion years from now will be slightly quieter than it is today. As some of the smaller galaxies merge or fade, the universe a trillion years from now will be much quieter, most of the small stars starting to dim. But right now, we are in the thick of it, the maximum complexity era. The era when the most stars are burning, when galaxies are still actively forming new generations of stars, when the universe has had enough time to produce the heavier elements necessary for rocky planets and liquid water and organic chemistry and life. If you were designing the universe with the specific intent of making it as interesting as possible, as rich with processes and structures and activity as it could ever be, you would design it to look more or less like it looks right now. You would design it to look like this, and here you are, inside it. The room you are lying in was built by people made of star-forged atoms on a planet, orbiting a middle-aged star in the outer arm of a spiral galaxy that is one of hundreds of billions of galaxies in the observable universe during the single most interesting epoch that universe will ever produce. You are not in a bad spot, you really are not. Now, the clock is running, and to understand what comes next, we need to think about what the stelliferous era actually looks like as it winds down. Not all at once, not dramatically. The universe does not do dramatic on these scales. It does patient, it does gradual, it does long, slow, almost imperceptible change stretched over timescales that make a human lifetime look like a photon crossing a room. But it is changing, even now. Right this moment, the universe is expanding. The fabric of space itself is stretching outward. And as it does, the galaxies beyond our local group are receding from us, redshifting, their light stretched to longer and longer wavelengths as they move away. In the far future, not the cosmically far future, the relatively near future, a few 100 billion years from now, most of the galaxies visible in our sky today will have receded beyond the cosmic horizon. The universe will look emptier. The local group will have merged into a single large elliptical galaxy, and the sky, already dark between the galaxies, will be darker still. But there will still be stars. For a while, there will still be stars, and that is where our journey goes next. Into the long, slow twilight of the stelliferous era. Into the last 100 trillion years of fire. 100 trillion years. The stelliferous era is a single word stretched across more time than a human mind can honestly hold. 100 trillion years. Written out, that is a 1 followed by 14 zeros. 100 million, thousand, and that number itself is somewhat conservative. It represents the approximate epoch, at which the last red dwarf stars will exhaust their fuel. Some estimates push it further, but 100 trillion years is a useful anchor, a number to hold, even if you cannot really hold it. Let's try anyway. The current age of the universe, 13.8 billion years, is already longer than most people intuitively feel. When you try to actually feel 13.8 billion years, most people hit a ceiling somewhere around 1 million, and everything after that is just a very long time. The mind substitutes a feeling for a number and calls it done. So let's approach this differently. Let's approach it by comparison. The first modern humans, people anatomically and behaviorally indistinguishable from you, appeared somewhere around 300,000 years ago. Recorded history, the written kind, goes back about 5,000 years. Civilization, in the sense of cities and organized agriculture, is maybe 10,000 years old. The entire span of recorded human history, every empire, every war, every discovery, every poem ever written, all of that fits inside 5,000 years. The Stelliferous era is 100 trillion years long. To put those two numbers next to each other, if the Stelliferous era were a mile long, recorded human history would be the width of a human hair, less than a human hair, a fraction of a human hair. And we are not even comparing it to the full timeline we are going to discuss tonight. We are going to go much further than the Stelliferous era. But for now, just that comparison. The fact that the era of stars, the era of light and fire and hydrogen burning in stellar cores, stretches 100 trillion years forward from where we sit, and that we are so early in it that we cannot meaningfully locate ourselves in it by comparison to human experience. We just have to accept that we are at the start, and it is a beautiful start, because right now the universe is rich. Right now there are stars of every size and age and temperature scattered through hundreds of billions of galaxies. There are massive hot blue-white stars burning so furiously they will exhaust their fuel in a few million years and die spectacularly. There are medium stars like our Sun, burning steadily for 10 billion years before their quiet deaths. And there are small, cool red stars, red dwarfs, burning so slowly and so efficiently that they will still be going long after the massive stars are dead and the Sun is a cooling white dwarf, and the galaxy has changed almost beyond recognition. Those small red stars are important to this story, very important. They are the last torches, but we will get to them. For now, let's follow the Stelliferous era forward. Let's watch it change. The first few 100 billion years are not dramatically different from today. Stars form and die. Galaxies evolve. The Milky Way and Andromeda, our nearest large neighbor galaxy, will collide and merge in about 4 or 5 billion years. A collision that sounds catastrophic, but is actually not violent in the way collisions normally are, because the space between individual stars is so vast that almost no stars actually hit each other. The two galaxies will pass through each other, distorting each other's shapes with gravity, and over the course of 1 billion years or so, they will settle into a single larger elliptical galaxy. Already there is a name for this future galaxy in some scientific discussions. Milkomeda, a blended name for a blended galaxy. And in that merged galaxy, the Sun will probably have died by then, or if not dead, very close to it. And Earth, if it is still recognizable as a planet, will have been scorched beyond anything habitable by the Sun's red giant phase. None of that is tonight's concern, but it is part of the shape of things. After a few trillion years, the rate of star formation begins to slow noticeably. The gas reserves in galaxies start to thin. The raw material for new stars gets harder to come by. Stars that die leave remnants, white dwarfs, neutron stars that lock away their mass in forms that do not easily recycle back into new stars. The rate of stellar birth slows, not dramatically, not all at once, but measurably, and as it slows, the population of stars shifts. The massive stars died long, long ago. The medium stars are dying. What remains increasingly is the slow and patient population of red dwarfs, small stars, dim stars. Stars that do not look impressive by any standard we would normally apply to stars. They are not hot enough to glow blue or yellow-white. They burn dull orange-red. From a distance, they are almost invisible without a telescope. But they are burning. Slowly, so slowly, they are burning, and they will continue to burn for a very long time. Red dwarfs are the most common type of star in the universe. There are more red dwarfs than all other types of stars combined, and their defining characteristic, the thing that makes them matter in this long arc of the future, is their extraordinary fuel efficiency. A star's lifespan is determined by two things: how much fuel it has and how fast it burns it. Massive stars have enormous amounts of hydrogen, but burn through it so quickly that they live only millions of years. Our sun has burned steadily for 4.5 billion years and has another 5 billion or so to go. But red dwarfs, small enough and cool enough to burn their fuel at a glacial pace, can sustain themselves for trillions of years. The smallest red dwarfs, the ones barely above the threshold of being a star at all, are estimated to be able to burn for somewhere around 10 trillion years. Some estimates go higher. There is genuine scientific uncertainty about the upper limit because no red dwarf has ever come anywhere close to the end of its life. The universe is not old enough yet. Every red dwarf that has ever existed is still burning, every single one without exception, because the universe is only 13.8 billion years old, and the shortest-lived red dwarf will outlast that by a factor of hundreds. We have never seen a red dwarf die. No one has. No one ever will. Not any human or human descendant alive today. Not for any reasonable interpretation of that phrase. The deaths of red dwarfs are theoretical, calculated, projected from first principles and stellar models, but not observed. And in the long, slow twilight of the stelliferous era, as the massive stars are long dead and the medium stars are all cooling white dwarfs, and the universe has changed beyond recognition. From how it looks tonight, those dim little red dwarfs will still be going, patient, slow, burning their hydrogen with such careful economy that they can keep the fire alive for timescales that dwarf everything that came before them. Picture the galaxy 10 trillion years from now. It is harder to picture than 10 trillion years in the past, because the past is at least knowable. We can point to evidence, to the light that has reached us, to the structural clues left by early stars. The future is inference and model and projection. But the picture that comes together from those models is something like this. The galaxy is older, quieter. Most of the star-forming regions that light up photographs of galaxies today, those brilliant blue-white regions where new stars are being born in clusters from collapsing gas clouds, most of those are gone. The gas has been used. The great nurseries are closed. What remains are the old stars, the survivors, scattered through a galaxy that has settled into a kind of quiet that it did not have in its youth. The brightest lights are gone, but there is still light, distributed, reddish, dim. Red dwarfs scattered through the darkness, billions of them, still burning, still patient, clustered in globular star clusters around the outer edges of the galaxy, sprinkled through the disk, drifting quietly through the dark. And at this point, the universe is 10 trillion years old. The current age of the universe, 13.8 billion years, compared to 10 trillion years is about 0.14%, a fraction of a percent. We are so early, and it keeps going. 20 trillion years, 30 trillion. The red dwarfs are still burning, but their numbers are thinning slowly. The ones that formed from the most gas, that were a little larger, a little more fuel-rich, those are the first to go. They swell slightly, not as dramatically as a sun-like star swells into a red giant, but they change. They exhaust their hydrogen, they cool and contract into white dwarfs, tiny, incredibly dense, still hot from the residual heat of their long lives, but no longer fusing anything, no longer producing new energy, just cooling. slowly cooling, 50 trillion years. The galaxy is becoming very sparse. The star formation rate is effectively zero at this point. No new stars have formed in a very long time. The stars that exist are the ones that will exist. The survivors, the red dwarfs that are still going, and the growing population of white dwarfs left by stars that have finished their lives. And here is a strange and interesting detail about those white dwarfs. They are not dark yet. They are cooling. They have been cooling since they formed. But cooling a white dwarf takes an extraordinary amount of time. A white dwarf is essentially a dead stellar core, carbon and oxygen mostly, compressed into something roughly the size of Earth with the mass of the Sun. It is incredibly dense, and that density means it holds heat the way a thick cast iron pan holds heat, far longer than you might expect. A white dwarf formed today will still be warm enough to faintly glow for hundreds of billions of years. In the cosmological literature, the eventual final state of a cold white dwarf, one that has radiated away essentially all its heat over hundreds of billions or trillions of years, is sometimes called a black dwarf. Not a black hole, a black dwarf, a cold, dark, dense remnant of a once-living star, an object the size of a planet with the mass of a star, floating in the dark, no longer radiating any significant energy. Here is the thing about black dwarfs, though. There are no black dwarfs yet. The universe is not old enough. Every white dwarf that has ever formed is still warm, still cooling, all of them, still radiating away their residual heat. The cooling process takes so long that not a single white dwarf in the history of the universe has had time to complete it. The coldest, oldest white dwarfs are merely very faint, not dark, not dead, still warm, still glowing faintly in infrared wavelengths. There are no black dwarfs yet. We are still so early, 100 trillion years. We arrive at last, at the rough end of the stelliferous era. The last red dwarfs are burning out now. The smallest ones, the most fuel efficient, the ones that started with just barely enough mass to ignite hydrogen fusion, are reaching the end of their lives. Not explosively, not violently. Red dwarfs do not go supernova. They are not massive enough. They simply exhaust their hydrogen, and the delicate balance between the fusion pressure pushing outward and the gravity pressing inward tips, and the star contracts. It fades, it dims. It becomes a white dwarf, an incredibly dense remnant, very different from the white dwarfs left by sun-like stars, but a white dwarf nonetheless. And when the last red dwarf dies, the stelliferous era ends. Not on a particular day, not at a specific moment that anyone could point to and say there. Right then, the last star went out. It is more like the dying of a fire in a fireplace. You watch the logs burn lower and lower. The bright orange dies back to red, the red to a dull glow. And at some point you realize the fire is out, and you cannot say exactly when the last ember became just ash. The stelliferous era ends like that, a long dimming, and then the last glow fades. And the universe is different now. Very different. It is worth sitting for a moment with what we are describing when we say the stelliferous era ends. We are saying no more hydrogen burning in stellar cores anywhere in the observable universe. No more new photons being produced by nuclear fusion. No more starlight. The photons that exist in the universe at that point are the last photons. Some of them have been traveling since the first stars formed, bouncing through the cosmos for nearly 100 trillion years. But no new ones are being made. The factory is closed, every galaxy is dark, every nebula is cold. The space between stars, which was always cold, always near absolute zero, always mostly empty, is now not between stars in any meaningful sense, because there are no stars. It is just space, just void, expanding silently in every direction. The universe is 100 trillion years old, and the lights have gone out. But it is not done, not even close to done. What comes after the stelliferous era is not nothingness. It is something quieter and stranger than nothingness. The universe in the degenerate era, The era that follows the stelliferous era is still full of things. Dense things, cold things, silent things. White dwarfs and neutron stars and brown dwarfs and black holes and cold rocky planets drifting through the dark. Just no light. And as we approach that transition, as the last red dwarfs begin to feel the weight of their own exhaustion, there is one particular star that deserves its own story. The last one, the very last star. There will be a last star, not metaphorically, not as a turn of phrase. An actual final star, a real, fusing, light-producing star, will burn somewhere in the universe, and it will be the last one. And when it goes out, an era of the cosmos that has lasted nearly as long as imagination can stretch will end. This is one of the quietest and strangest ideas in all of cosmology, and it is worth spending some time with it. We do not know which star it will be. We cannot know. The identity of the last star is hidden in trillions of years of evolution that we cannot predict at that resolution. We know the type of star it will be. Almost certainly a red dwarf, almost certainly one of the smallest and least luminous of the red dwarfs, a type called an M dwarf in the stellar classification system. We know approximately when it will happen, within a reasonable range of uncertainty, but we do not know which specific star, in which specific remnant galaxy or drifting stellar cluster will hold the last fire, and somehow that anonymity makes it more moving, not less. Think about the Sun for a moment. It is a fairly typical star, slightly above average in mass for a star. It will live about 10 billion years total. It formed 4.6 billion years ago in the collapse of a gas cloud in this galaxy. It will die in about 5 billion years, after expanding into a red giant and then shedding its outer layers. Its death, while dramatic from a planetary perspective, is routine from a cosmic perspective. Billions of stars have died this way before. Billions more will die this way. The Sun will not be the last star. The last star will be much smaller and much dimmer and much slower. It will have formed from gas clouds in the earlier universe, possibly billions or even trillions of years ago. It will have been burning for an incredibly long time before its final moments, because red dwarfs burn so slowly and so steadily that the ones burning today will still be burning when the sun is a cold black dwarf. The last star will be lonely. That word, lonely, has to be stretched to fit the scale we are talking about. Not lonely the way a person is lonely. Lonely in the sense of isolated. Lonely in the sense that the universe around it will be very, very different from the universe we know. By the time the last red dwarf is burning out its final reserves of hydrogen, the universe will be unimaginably emptier than it is now. The large-scale structure that we can see today, the cosmic web, the filaments and sheets of galaxies connected by gravity, the great walls and voids that give the universe its texture at the largest scales, that structure will be long disrupted. Individual galaxies will have long since merged or dispersed. Stars will have been flung out of galaxies by gravitation interactions over the preceding trillions of years, scattered as solitary wanderers through the void. Globular clusters will have dissolved. The orderly arrangement of stars in galactic disks will be just a memory encoded in nothing. The universe will be dark and vast and mostly empty, and in some corner of it, a tiny dim red star will still be burning. Let's think about what that actually looks like. A red dwarf, even a healthy one at its peak, is not impressive by our sun standards. The faintest red dwarfs have luminosities about 1/10,000th that of the sun. If you put your hand up toward the sky with one of these stars as your sun, it would look more like a large glowing coal than a sun. The sky would be dark even at midday. If there were a planet orbiting it in the habitable zone, that planet would need to orbit very close, much closer than Mercury orbits the Sun, to be warm enough for liquid water. And such a planet would likely be tidally locked, one face always toward the star, always bathed in that dim red glow, the other face always turned away into perpetual darkness. The last star will be something like this, not brilliant, not blazing, dim and patient and slow, burning hydrogen into helium at a rate so modest that it can sustain the process for trillions of years without straining. But there is something going on inside it that is genuinely interesting. As a red dwarf burns, it is convective throughout. Unlike our Sun, which has a convective outer layer and a non-convective radiative core, a red dwarf's entire interior is convective. Material circulates continuously throughout the star, mixing hydrogen from outer layers down into the core. This means a red dwarf can use essentially all of its hydrogen as fuel, not just the hydrogen in its core. It is a more efficient fuel consumption process than what happens in larger stars, and it is why they last so long. But even this efficiency has limits. Gradually, over trillions of years, the hydrogen fraction decreases. Helium accumulates. Not quickly, slowly with an almost geological patience. The core temperature adjusts. The luminosity changes slightly, but the star holds on. It is not ready to go. And as it burns, it is the only source of light anywhere in the observable universe. That is a fact worth sitting with. The last star, during its final billions of years of life, after all its companions have gone, is producing essentially all the visible light anywhere. Everything else is dark. White dwarfs glowing faintly in infrared, too dim to see with unaided eyes that no longer exist to see them. Black holes consuming whatever drifts within their reach, producing nothing visible. Cold brown dwarfs drifting in the dark, never quite massive enough to have fused hydrogen at all. Cold rocky objects drifting on ancient orbital paths around cold stellar remnants. Just this one star, just this one small, dim, patient burning point of light in an ocean of dark that extends in every direction without limit. The concept of a sky has no meaning anymore. There is no planetary surface we can stand on with the right atmospheric conditions and look up and call it a sky. But if there were some impossible observer positioned near the last star, the sky would be perfect black in every direction, except for that one dim reddish point. No other stars, not even distant ones. The universe has expanded so much, and the light travel time has become so vast, that even if somehow other sources of light existed elsewhere, their light would never reach this place. The last star sits inside its own light cone, visible to itself and to whatever is immediately nearby and to nothing else. It burns. For billions of years it burns. And then, gradually, the hydrogen fractions in its interior reach the tipping point. The rate of fusion begins to drop, not precipitously, not in a single dramatic collapse, just slowly, the fire dwindling, like a gas burner with the valve being turned down, very, very slowly over millions of years. The luminosity decreases. The star cools slightly at its surface. The reddish glow becomes a deeper, darker red. Some models suggest that the most fuel-efficient red dwarfs, as they exhaust their hydrogen and become helium-dominated, pass through a phase of becoming what is sometimes called a blue dwarf, hotter and bluer than in their youth, burning helium under different conditions, before finally collapsing into a white dwarf. This is theoretical, because no red dwarf has ever reached this stage. But if it is true, there is something poignant about it. The last star might, in its final phase, burn brighter and hotter than it ever has in its long life. A brief climax before the end, a brief blue flame, and then the fusion stops. The outward pressure that fusion provides, the radiation pressure that has been holding the star up against its own gravity for trillions of years, drops. Gravity wins. Finally, the way gravity always eventually wins. The star contracts, compresses. It is not massive enough to collapse further than a white dwarf stage, so it stops there. A dense, hot, slowly cooling remnant. Small as planets go, dense as imagination struggles to hold. The last light goes out. This is not a dramatic event. There is no explosion, no final flash. No goodbye signal sent across the cosmos. The last star simply fades. The reddish glow of its surface dims to orange, dims to a dull red, dims to infrared, dims below detection. The stelliferous era ends, not with a bang, with a cooling. Right now, as you are lying there, this is 100 trillion years away. Your room is warm. The air is moving with your breathing. If you could step outside this moment and look up at a dark sky, you would see stars, hundreds, maybe thousands of them, and each one is a furnace in the dark, burning hydrogen, producing light, participating in the great stellar era of the cosmos. The last star is not a tragedy. I want to be careful about that. There is something deeply human about looking at an ending and calling it sad. But the last star is not sad. It is the natural conclusion of a process that has been running for 100 trillion years. It is the final expression of an era defined by light, and its ending is not the end of the universe. The universe will continue for timescales that make the stelliferous era look brief. What comes after is not nothing. It is the degenerate era, and the degenerate era has its own strange beauty, its own cold patient processes, its own extraordinary timeline. The last star cools, and the universe, now dark in a way it has never quite been before, enters a new phase. A phase of white dwarfs and neutron stars and black holes and cold, dark remnants drifting through infinite expanding space. The stelliferous era is over, and the universe has barely begun. The universe is dark now. Not dark the way a room is dark when you turn off the lights. Not dark the way a night sky is dark between the stars. This is a different kind of dark, a structural dark. A dark that is not the absence of light in a place where light used to be, but the absence of anything that could produce light anywhere. The factory is closed. The last fusion reactor has gone cold. The photons that remain in the universe are ancient, stretched, scattered, remnants of processes that ended long ago. No new ones are being made. This is dark in the way that silence is not just the absence of sound, but the condition of a space where nothing is moving. The degenerate era. It is a strange name if you think about it. Degenerate sounds like a judgment, like a decline. But in physics, degenerate has a specific and almost poetic meaning. Degenerate matter is matter in a state governed by quantum mechanical pressure rather than thermal pressure. Ordinary matter, the matter in stars, in gas clouds, in you, is held up by thermal pressure. Heat the matter, and it pushes outward. Cool it down, and it collapses. But degenerate matter is different. A white dwarf is supported not by heat, but by something called electron degeneracy pressure. A quantum mechanical effect that essentially says two electrons cannot occupy the same state at the same time, so they resist being compressed together regardless of temperature. This pressure does not depend on heat. A cold white dwarf is just as hard as a hot one. That is what the degenerate era is named for. Not a falling apart, a holding on. The remnants of the stellar era, supported by quantum mechanics rather than fire. The universe after the last star is populated by these remnants. Let's catalogue them, slowly, one by one. White dwarfs. These are the most common remnants. Any star that began its life between roughly 8 solar masses and some lower limit, and the lower limit covers the vast majority of stars that have ever existed, ends its life as a white dwarf. Our sun will become one. Most of the stars you can see tonight will eventually become one. By the time the degenerate era is fully underway, the universe is filled with white dwarfs, billions upon billions of them. Some still warm enough to glow faintly in infrared, the older ones already cooling toward the temperatures of interstellar space. At 100 trillion years, the white dwarfs are at various stages of cooling. The oldest ones, those formed in the first few billion years of the universe from the earliest generations of stars, have had the most time to radiate their heat away. They are the coldest, dimmest, closest to that theoretical final state of the black dwarf. But even these have not completed the journey. The cooling is so slow that even after 100 trillion years, not all white dwarfs have become fully cold. They are cool, very cool, but still, on some technical level, warmer than absolute zero, which is a strange thought. At absolute zero, 0 Kelvin, minus 273 degrees Celsius, the point at which all thermal motion ceases. No vibration, no movement, perfect cold. Absolute zero is not achievable in practice. You can approach it asymptotically, but never quite reach it. Even in the emptiness of intergalactic space, the universe maintains a background temperature just barely above absolute zero, a residual warmth from the cosmic microwave background radiation, the ancient echo of the Big Bang itself. But even that background temperature is falling. As the universe expands, the cosmic microwave background radiation redshifts. Its photons stretch to longer and longer wavelengths. Its temperature drops. In the early universe, the CMB temperature was thousands of degrees. Today it is about 2.7 Kelvin. In the far future, in the degenerate era, it will be a tiny fraction of a degree, not zero, but approaching zero asymptotically, the way everything in physics approaches its ultimate limits. So the degenerate era is cold. It is very cold, getting colder, but not empty, neutron stars. These are the remnants left by stars too massive to become white dwarfs, but not quite massive enough to collapse all the way into a black hole. When a star between roughly 8 and 20 solar masses exhausts its fuel, it does not go quietly. It collapses catastrophically and then rebounds in a supernova explosion. One of the most energetic events in the known universe, briefly outshining entire galaxies. The outer layers are blasted away. The inner core survives, compressed so intensely by gravity that electrons and protons are forced together to form neutrons. The result is a neutron star, an object typically about 20 kilometers in diameter, the size of a city, with a mass 1 to 2 times that of the Sun, 20 kilometers across with the mass of the Sun. A teaspoon of neutron star material would weigh billions of tons. Neutron stars are supported against further collapse by neutron degeneracy pressure, the same quantum principle as electron degeneracy pressure in white dwarfs, but operating at a more extreme level. They are incredibly dense. They sometimes spin hundreds of times per second. They can have magnetic fields trillions of times stronger than Earth's. Some of them emit beams of radiation that sweep through space like lighthouse beams. These are what we call pulsars. In the degenerate era, the neutron stars are cooling. They have been cooling since they formed, some of them for nearly 100 trillion years. Their surface temperatures have dropped from the extraordinary millions of degrees they had at birth to something far lower. They spin more slowly now. The gradual loss of rotational energy over trillions of years has slowed even the fastest pulsars to a crawl. They no longer emit the intense radiation they once did. They are quiet, patient, dense and cold and dark, drifting through the void, brown dwarfs. These are a category of object that never quite became stars. A brown dwarf is a body with more mass than a planet, but not enough mass to sustain hydrogen fusion. Somewhere between about 13 and 80 times the mass of Jupiter. They are substellar. They are not stars. They never burned. Some of them, the most massive ones, generated a brief flicker of deuterium fusion early in their existence. But deuterium is rare, and that fusion ended quickly. For the rest of their existence, they have been slowly cooling, radiating away the heat of their formation, drifting through the dark. In the degenerate era, the brown dwarfs are very cold. They have been cooling for 100 trillion years. Their surface temperatures, which were already low when they formed, are now indistinguishable from the surrounding void. They emit essentially no radiation at any wavelength detectable by any reasonable instrument. They are dark, they are dense, they exist, but they do not announce themselves, and there are a lot of them. Brown dwarfs may be as common as regular stars, or even more common. The galaxy that we live in probably contains hundreds of billions of them, and most of them formed early in galactic history and have been cooling ever since. In the degenerate era, they are just cold, dark masses drifting, cold planets, cold moons, cold asteroids. In the degenerate era, the planets that orbited the stars are still out there, or some of them are. over hundreds of trillions of years, gravitational interactions between objects in stellar systems have disrupted many of those orbits. The same kind of gravitational perturbations that occasionally send comets into the inner solar system, scaled up over cosmological time, will have either ejected most of them from their parent systems, sending them drifting as rogue planets through the void, or crashed them into their central remnant. But some fraction will survive: cold rocks, dark frozen worlds. No atmosphere. Any atmosphere they had is long gone, frozen onto the surface or lost to space. No geological activity, their interiors long since cooled and solidified. Just cold, dense masses drifting in the dark. They do not glow. They do not move in ways that change the larger picture. But they exist. And black holes. We will spend significant time with the black holes shortly, because they are the dominant feature of the era that comes after the degenerate era. But they exist in the degenerate era too. They have existed since the first massive stars died and collapsed, billions of years before the stelliferous era ended. In the degenerate era, the black holes are largely quiet, not consuming much because there is not much to consume. The gas and dust that once fed them is gone. They drift, they wait, patient in a way that has no human analogue. Now, here is something that the degenerate era contains that deserves special attention. Right now, as you lie there, the room around you is warm. The air is breathable. Outside, even if it is dark, there is a sun that will rise. Somewhere in the galaxy, new stars are forming. The universe is busy and bright and full of processes that we take entirely for granted because they have always been there, every day of every life that has ever been lived on this planet. In the degenerate era, none of those processes exist. No fusion, no stellar winds, no planetary weather, no liquid water anywhere, no chemistry that requires energy input, because there are no accessible energy gradients. The temperature everywhere is approaching absolute zero. The universe is a vast, cold, dark, nearly static collection of dense objects drifting through expanding space. And it is extraordinary in its way, because it is still not done. The degenerate era is not the end. The degenerate era is a long pause between one kind of story and another, and the degenerate era itself will last an enormous amount of time. We are talking about timescales that extend from 100 trillion years to somewhere around 10 to the 37th power years. A number written as 1 followed by 37 zeros. During that time, the white dwarfs continue cooling. The neutron stars continue their slow decay. The brown dwarfs drift. The planets drift. Something else is happening too: proton decay. This is a theoretical process. It has never been observed, and some extensions of physics suggest it may not happen at all, or may happen on timescales far longer than current estimates. But some models of particle physics predict that protons themselves, the fundamental building blocks of atomic nuclei, the things that make atoms atoms, are not stable forever. They have an extremely long half-life, extremely long, but eventually, given enough time, they may decay. If protons decay, then all ordinary matter, all the white dwarfs and neutron stars and cold planets and brown dwarfs, everything made of atoms, will eventually dissolve, not dramatically, not in a single moment. Slowly, one proton at a time, the substance of the degenerate era will decay away. White dwarfs will erode. Cold planets will lose their mass. Neutron stars, which are made of neutrons rather than protons, would be affected differently and on different timescales. But the general trend, if proton decay occurs, is that all the remnants of the stellar era will eventually dissolve. This happens in current theoretical estimates at around 10 to the 37th power years, give or take. If we write out the degenerate era in years, it runs from about 10 to the 14th power to about 10 to the 37th power years. That is a span of time that is so much larger than the stelliferous era that the stelliferous era, 100 trillion years of stars, is a brief introduction, a prologue, And all of that before we get to the black holes. The white dwarfs cool toward darkness. The neutron stars slow. The cold remnants drift through expanding space that grows emptier every passing eon. And the black holes, patient and massive and silent, wait. They have been waiting since the first massive stars died. They have consumed whatever fell within their reach. Gas clouds, stars, other black holes merging in the cataclysmic events called gravitational wave mergers. In the early universe, the supermassive black holes at the centers of galaxies were surrounded by food, accretion disks of gas, stars spiraling too close, entire galaxies merging and feeding the central engine. But in the degenerate era, the food has been consumed. The accretion disks have long since cleared. The central black holes sit in emptiness, waiting, and waiting is what they do, until the degenerate era ends, and the black hole era begins. Everything that was not a black hole is either gone or going. The white dwarfs, if proton decay is real, have slowly dissolved. The neutron stars, the cold planets, the drifting rocks, the atoms of which they were made have decayed, one by one, over timescales that beggar description. The universe has been emptying itself of ordinary matter for eons beyond counting. And what is left, what has survived all of this dissolution and expansion and cooling, is the black holes. This is the black hole era. And the black hole era dwarfs everything that came before it. Let's talk about what a black hole actually is, because the word gets used so often that it can start to feel like it has been emptied of its strangeness. A black hole is a region of space-time where the curvature of space has become so extreme, where so much mass has been compressed into such a small volume that the escape velocity exceeds the speed of light, which means nothing can escape, not matter, not radiation, not light. The boundary of this region is called the event horizon, not a physical surface, not a wall, just a threshold, a mathematical boundary in space, beyond which the rules change. Inside the event horizon, all paths lead inward. There is no direction that leads out. You fall in. Everything falls in. The black hole sits at the center of its event horizon, and it waits. In the black hole era, the supermassive black holes are the dominant objects in the universe. They formed from the original galactic centers, regions where the density of matter was so extreme in the early universe that black holes formed and grew, consuming gas and stars and other black holes for billions of years. The most massive black holes known in today's universe are on the order of tens of billions of solar masses. A single black hole with the mass of tens of billions of suns contained within a region smaller than our solar system. In the black hole era, these objects remain, and they are alone. The universe, by the time the black hole era is fully underway, is extraordinarily empty. The expansion of space has continued for so long that whatever was not gravitationally bound together has receded so far that it might as well not exist. The local group, the gravitationally bound cluster of galaxies that includes the Milky Way and Andromeda and a few dozen smaller galaxies, will have merged into a single elliptical remnant galaxy by this point. And that merged remnant will itself have slowly lost its stars to evaporation and orbital decay over the course of the degenerate era. Galaxy evaporation is a thing, by the way. Over sufficiently long timescales, tens of trillions of years, say, a galaxy does not stay a galaxy. The stars in it interact gravitationally with each other, constantly, subtly, the way gas molecules in a container interact. In gas, these collisions result in some molecules going faster and some going slower, and occasionally a molecule near the surface moves fast enough to escape the container. That is evaporation. The same process happens in galaxies. Gravitational interactions between stars result in some stars gaining energy and some losing it. The ones that gain energy can escape the galaxy entirely, drifting off as rogue stars into the void. The ones that lose energy sink deeper into the galaxy's center. Over enough time, most of the stars evaporate out of the galaxy. the ones that remain spiral inward toward the central black hole and are eventually consumed, and the black hole grows. So by the time the black hole era is fully established, after the degenerate era has run its course and ordinary matter has either decayed or been consumed, what remains is largely the black holes, various sizes, various ages, spread through the vastness of a universe that is still expanding, still growing larger, still cooling toward that asymptotic approach to absolute zero. And the black holes are doing not very much. This is one of the genuinely strange things about the black hole era. Black holes are associated in the popular imagination with violence, with devouring, with destroying, with the catastrophic end of anything that comes near them. And in the active early universe, the supermassive black holes were active. They consumed. They radiated from their accretion disks. They powered some of the most energetic phenomena in the cosmos. Quasars, active galactic nuclei, jets of particles accelerated to near the speed of light and blasted across millions of light years. But in the black hole era, there is nothing to consume. The food is gone. The black holes sit in empty space. Occasionally, rarely, over these vast timescales, a cold object drifts within reach and is consumed. But mostly they wait. They do not radiate. They do not glow. They are dark. They are silent. They are, in some sense, the ultimate expression of everything the universe has been doing since the Big Bang. Collapsing matter, compressing it, removing it from the accessible universe, and they are patient. Here is a way to think about the patience of a black hole. The current age of the universe is about 13.8 billion years. A billion is 1,000 million, 13.8 billion years. That is how long everything that has ever happened has taken. Every galaxy formation, every star birth and death, every planet forming from a disk of gas and dust, every ocean, every storm, every living thing, all of it in 13.8 billion years. The black hole era lasts considerably longer. How long? Well, this is where numbers start to lose their meaning in the most absolute possible way. The black hole era, from the end of the degenerate era to the evaporation of the last black hole, spans timescales measured not in billions or trillions, but in numbers like 10 to the 67th power years for the smallest black holes. The stellar mass ones formed from the collapses of individual massive stars. Those will evaporate through a process we will describe shortly in roughly 10 to the 67th power years. 10 to the 67th, a 1 followed by 67 zeros. The current age of the universe is roughly 10 to the 10th power years. The stelliferous era ends at roughly 10 to the 14th power years, and the smallest black holes evaporate at 10 to the 67th power years. Each step is not a little longer than the previous. Each step is incomprehensibly longer. Going from the current age of the universe to the end of the stelliferous era is already a leap of 10,000 times. Going from the end of the stelliferous era to the evaporation of the first black holes is a leap of 10 to the 53rd power times. There is no human experience that scales to this. And the supermassive black holes, the ones that have consumed entire galaxies worth of matter over billions of years, those take even longer. Much longer. We will get there. But let's stay for a moment in the black hole era and feel the scale of it. You know how sometimes you look at a map and realize that what looked like a small country is actually the size of a continent? The black hole era is like discovering that what looked like a universe is actually a single atom in a much larger universe. Every era we have described so far, the stelliferous era, the degenerate era, is a rounding error in the ledger of the black hole era. The universe spends most of its existence in this state, mostly dark, mostly empty, mostly just a collection of black holes drifting through expanding space, each one an island unto itself, separated by distances so vast that even at the speed of light, you could never travel from one to another in any reasonable time. Mostly quiet, except for a whisper, A very faint, very slow, very patient whisper. Hawking radiation. That is what will end the black hole era. That is what will eventually, over timescales that are to the current age of the universe, as the universe is to a single heartbeat, evaporate every black hole down to nothing. A whisper. Let's talk about it. Stephen Hawking was 32 years old when he worked out that black holes are not truly black. This was 1974. The physics community had been operating under the assumption that black holes, once formed, were permanent. They consumed matter and radiation. They produced nothing. They were, in the language of thermodynamics, sinks, one-way doors through which mass and energy entered the universe accounting books and never returned. There was something philosophically troubling about this. It seemed to violate certain deep principles about how information behaves in the universe. But the math seemed clear. Once inside the event horizon, nothing comes out. Hawking showed this was not quite right. The argument he made is subtle and requires holding two ideas together simultaneously: quantum mechanics and general relativity. These are the two great pillars of modern physics, and they are famously awkward with each other. General relativity describes gravity and the large-scale structure of space-time beautifully, but treats the world as continuous and smooth. Quantum mechanics describes the behavior of matter at the smallest scales beautifully, but insists on a universe that is fundamentally probabilistic and grainy. The reconciliation of these two frameworks is one of the great unsolved problems in physics, and it is still unsolved. Hawking found a place where they collide. Here is the idea, and I want to try to explain it not in the textbook way, but in a way that feels real. Quantum mechanics tells us that empty space is not truly empty. This sounds absurd. Space is space. Emptiness is emptiness. But at the quantum level, the vacuum, even perfect vacuum, even the absolute emptiness of the void, is seething with activity. Not the activity of particles exactly. More like the activity of potential particles. Quantum field theory describes the universe in terms of fields that permeate all of space, and those fields are never truly calm. They fluctuate. They experience what are called quantum fluctuations, tiny ripples in the energy of the field that can briefly manifest as pairs of particles. A particle and its antiparticle that appear spontaneously out of nothing, and then, a moment later, annihilate each other and vanish back into nothing. Virtual particles, these are sometimes called, not real particles in the ordinary sense. They borrow energy from the vacuum briefly and then return it. They cannot be detected directly. They are a consequence of the fundamental uncertainty at the quantum level, the fact that you cannot know both the energy of a field and its rate of change simultaneously with perfect precision. In ordinary empty space, these virtual particle pairs appear and vanish so quickly that the net effect is nothing. They cancel. The vacuum is still effectively empty on any measurable scale. But near a black hole's event horizon, something different happens. A virtual particle pair appears. One particle appears on the outside of the event horizon. One particle appears on the inside. In ordinary space, they would annihilate each other a moment later. But the event horizon is a one-way membrane. The particle inside the event horizon cannot come back out. It is already inside the region of no escape, and so it cannot return to annihilate its partner. The particle outside the event horizon finds itself without its partner. It has energy borrowed from the vacuum. Normally, it would have to return that energy, but its partner has been swallowed by the black hole. And the black hole, to balance the energy books, loses a tiny amount of mass. The energy has to come from somewhere. It comes from the black hole itself. The particle outside drifts away. From the perspective of a distant observer, it looks exactly as though the black hole has emitted a particle, as though radiation has emerged from what was supposed to be a perfect sink. This radiation, the steady, extremely faint, extremely slow emission of particles from black holes through this quantum process, is Hawking radiation. The implications are extraordinary. The first implication: black holes are not permanent. They lose mass through Hawking radiation, very, very slowly, vanishingly slowly. A black hole the mass of our Sun would lose mass through Hawking radiation at a rate so slow that the number defies ordinary expression. Something like 10 to the minus 28th power of a gram per second. Not detectable, not even remotely measurable with any current or foreseeable technology, but real, happening. The mass is leaving, one quantum event at a time. The second implication: the rate of mass loss is not constant. As a black hole loses mass, its temperature increases. This sounds backwards. We think of cooling things losing heat, not gaining it. But black holes are strange. The smaller a black hole is, the higher its Hawking temperature. A supermassive black hole has a Hawking temperature so close to absolute zero that it is, for all practical purposes, indistinguishable from absolute zero. The cosmic microwave background radiation, even in the current universe, is warmer than the Hawking temperature of a supermassive black hole, which means, strange as this is, that supermassive black holes are currently absorbing more radiation from the CMB than they emit in Hawking radiation. They are right now technically gaining mass slightly, not losing it, but the CMB temperature is falling with the expansion of the universe. At some point in the far future, the CMB temperature will fall below the Hawking temperature of even the supermassive black holes, and at that point they will begin their true evaporation. And as they evaporate, as they lose mass, their temperature rises. And as their temperature rises, they lose mass faster, which raises their temperature further, which makes them lose mass faster still. It is a slow acceleration. For most of the evaporation process, the mass loss is so slow it is effectively zero. Then, near the very end, in the last fraction of a second, cosmologically speaking, the black hole reaches a critical mass, a critical temperature, and the process accelerates dramatically. The last moments of a black hole are not a quiet fading, but a burst of radiation, a final flash of Hawking radiation as the remaining mass evaporates in what is sometimes called the black hole's last gasp. Not an explosion in any normal sense, but something, a brief something in an otherwise unbroken silence. Hawking also showed, and this is the part that troubled him and has troubled physicists ever since, that Hawking radiation appears to be thermal, random, without information. When a black hole evaporates, the radiation it produces does not, as far as we can tell, encode any information about what fell in, the star that collapsed to form it, the gas and dust it consumed, the photons it absorbed, the matter it swallowed. All of that information appears to be gone, lost, not transformed, not scrambled but recoverable, gone. This is the information paradox. It bothers physicists deeply. One of the foundational principles of quantum mechanics is that information is conserved, that the state of a system at any time in principle encodes its entire history, that the equations of quantum mechanics run both forward and backward, that nothing is truly lost. But Hawking radiation seems to erase information. It seems to be a true one-way door, which means something is wrong, either with our understanding of Hawking radiation, or with our understanding of quantum mechanics, or with our understanding of something deeper that we have not yet identified. This is an open problem, and there is something wonderful about an open problem. It means there is more to understand. The universe is not yet fully mapped. Even at the end of the universe, in the slow evaporation of the last black hole, there are questions we have not yet answered, mysteries that will never be resolved, because the end of the black hole era is not a place anyone will ever observe directly, but mysteries that can still be engaged, still be thought about, still be a source of awe. Hawking died in 2018. He was diagnosed with motor neuron disease at 21 and told he had perhaps 2 years to live. He lived to 76. He worked on this problem, the information paradox, the nature of Hawking radiation, the behavior of space-time at extreme conditions, for the last decades of his life. He made proposals and withdrew them. He shifted his position. He remained engaged with the mystery. In some sense, Hawking radiation is one of the most remarkable discoveries in the history of physics, a consequence derived purely from theory, from holding quantum mechanics and general relativity together at the edge of a black hole and watching what the math produces. It has never been directly observed. The signal is too faint. The black holes we know of are too cold. But the theory is almost universally accepted among physicists as correct. And if it is correct, it means black holes are not permanent. They are impermanent. Like everything else, just very, very, very slowly impermanent. And as the universe ages into the black hole era, as the last white dwarfs cool toward darkness, and the last of the ordinary matter has either decayed or drifted away, the only process still operating anywhere is the extremely slow, extremely quiet, extremely patient evaporation of black holes through Hawking radiation, one quantum event at a time, one tiny increment of mass at a time, over timescales that are to the current age of the universe as, well, as a number that does not translate into human language. The black holes are evaporating. The smallest ones will go first, and then the larger ones. And at the very end, the last of the supermassive black holes will reach the final stages of its evaporation. And for a brief flash of cosmic time, there will be something. A faint glow of Hawking radiation, the last process in the universe, and then that too will be done. But we are not there yet. Let's go there now. The number is so large that we have to approach it sideways. Let me try to give you a sense of what we are talking about when we talk about the time it takes for the last supermassive black hole to evaporate through Hawking radiation. Not the number itself, though I will get to the number, but a feeling for what kind of number it is. You know how, in ordinary life, very large numbers still feel manageable because they refer to things you can count. You can count to 100. You can imagine 1,000. You can visualize 1,000,000 in some vague way, 1,000,000 grains of sand, $1,000,000. You can get a rough intuitive sense of 1,000,000,000 if you think about it as 1,000 millions. 1,000,000,000,000 you can technically define, but not really feel. After 1,000,000,000,000, most people are just waving their hands at the concept of a very large number and nodding. Now, take that hand-waving gesture and imagine doing it not once but dozens of times. Each time you wave your hand, you are not adding more zeros to the number, you are multiplying by a power of 10. Each additional zero does not make the number a little bigger, it makes it 10 times bigger than the last adjustment. And each of those adjustments is already at a scale where the word bigger has lost its meaning. The lifespan of a supermassive black hole, one with a mass of around 1,000,000,000 solar masses, which is on the large end, but not the most extreme we know of. Before it evaporates plants completely through Hawking radiation, is approximately 10 to the 83rd power years. A 1 followed by 83 zeros. This is the number. It is not a number that rewards attempts to visualize it. But let's try to contextualize it. The observable universe contains somewhere between 10 to the 78th and 10 to the 82nd power atoms. This is an estimate, obviously. We cannot count atoms in the observable universe, but it is the best current estimate from cosmological models. Somewhere around 10 to the 80 power atoms in everything we can see, in all the galaxies and stars and planets and gas clouds and dust and everything else. The evaporation time of a large supermassive black hole is longer than the number of atoms in the observable universe. If you wrote a 0 on every atom in the observable universe, every atom in every star, in every galaxy in the entire cosmic web, you would not have enough atoms to write this number down. That is the timescale we are talking about, and the most massive black holes we know of, the monsters at the centers of the largest galaxies, tens of billions of solar masses, take even longer. Their evaporation time is estimated at around 10 to the 100 power years. You will sometimes see this written as a googol, because 10 to the 100th power is the number that inspired the name of a certain internet company, a Google years. And even that is not the end. It is just the rough estimate for the most extreme cases we can currently calculate. The universe will spend a Google years, roughly, waiting for the last black holes to finish evaporating. And during those Google years, what is happening in the universe? Almost nothing. The universe in the late black hole era is not the degenerate era anymore. The white dwarfs have long since either cooled to black dwarfs and then dissolved through proton decay or similar processes, or they have been consumed by black holes. The neutron stars are gone, the planets are gone, the ordinary matter is essentially gone. What remains is the black holes themselves, spread through a universe that is still expanding, still growing vaster and emptier, and the extremely faint radiation they produce through the Hawking process. The temperature of a large black hole's Hawking radiation is mind-bendingly small, something like 10 to the minus 29 Kelvin for a solar mass black hole, and supermassive ones are far colder than that. We are talking about temperatures so close to absolute zero that even the universe's background temperature in the far future, itself already a tiny fraction of a degree, would be warmer. The universe during the black hole era is a vast, dark, cold, nearly silent place in which the only thing happening anywhere is the imperceptibly slow loss of mass from black holes through a quantum process that produces the faintest possible radiation. And it goes on for a Google years, and then, the last supermassive black hole reaches the point where its mass has decreased to the point where the process begins to accelerate. The Hawking temperature rises as the mass falls. The radiation increases. The mass falls faster. The temperature rises faster. The positive feedback loop of evaporation reaches its final stage. Picture this: a universe that has been dark and cold and effectively unchanging for a Google years. A universe in which no event has occurred that would register as an event by any normal standard. No light, no fusion, no chemistry, no process of any kind except the slow quantum whisper of Hawking radiation from the last black holes. And now the last black hole, the most massive, the one that has outlasted everything, the remnant of 1 billion suns compressed into a point of infinite density. Now it reaches the final phase. The radiation increases, not dramatically, not all at once, over millions of years at first, then thousands, then shorter and shorter intervals as the mass decreases and the Hawking temperature climbs. The radiation is not visible light for most of this process. It is not anything that would strike the human eye as a glow. It is radiation at extremely long wavelengths, gradually shortening as the temperature increases. Long radio waves first, then shorter, the spectrum climbing as the black hole shrinks. And then, in the final seconds, the literal final seconds, the temperature reaches the point where the radiation is extraordinarily intense. Gamma rays, the full electromagnetic spectrum all at once. A burst of energy from the last evaporation. The last something in a universe that has been nothing for a very long time, and then it is gone. The black hole is gone. There is no black hole anywhere in the universe. For the first time in nearly a Google years, actually, for the first time since the first massive star died and collapsed, which was billions upon billions of years ago, so far in the past that the past barely applies as a concept. There are no black holes anywhere, just the residue of the evaporation. Photons of extraordinary length, particles at the extreme low end of energy, the last Hawking radiation from the last black hole, spreading outward through expanding space at the speed of light, growing redder and longer and fainter as the universe continues to expand, and nothing else. Stillness. A kind of stillness that the universe has never known before this moment. Not the stillness of the cold degenerate era, which still had white dwarfs cooling and neutron stars drifting. Not the stillness of the late stelliferous era, which still had the last red dwarf burning. The absolute, structural, irrevocable stillness of a universe in which there are no longer any physical processes of any kind occurring anywhere. The era of black holes is over. The dark era begins. And the dark era is so still, so final, so complete in its silence that the word silence does not actually cover it. The word does not exist. We would need a new word, and there is no one left to coin it. There is a word in physics for what the universe becomes after the last black hole evaporates. The word is nothing. Not nothing in the philosophical sense, the rich debated sense where scholars across centuries have argued about whether true nothing can exist, whether the absence of being has any meaning, whether nothingness is itself a kind of something, not nothing in the way a cleared room is nothing, where the nothing implies that something was there before and could be there again, nothing in the strict physical sense, no matter organized into any structure, no energy available at any gradient, no atoms, no molecules, no electrons bound to nuclei, no processes driving any reaction, no information arranged into any pattern above the thermal noise floor of a universe at near absolute zero temperature. Just the last thin, cold, barely there scattering of elementary particles at the very bottom of the energy scale, drifting through a universe that is still expanding, still growing vaster and emptier with every passing eon, still cooling toward an absolute zero. It will approach forever without ever quite arriving. This is the dark era, and the dark era is not a transition phase. It is not a waiting room for something else. It is not a pause before the next act. The dark era is the final condition of the universe. It is what the universe has been becoming since the moment of the Big Bang, when all the processes we have been describing tonight, stellar evolution, black hole dominance, Hawking evaporation, were set in motion. Everything before the dark era was the universe arriving at this. The dark era is not what happens after the universe ends. The dark era is how the universe ends. Slowly, permanently, with no drama at all. Let's stay with what actually remains. After the last black hole evaporates in that faint final burst of Hawking radiation, the universe contains a thin and extraordinarily sparse collection of elementary particles, not atoms. Atoms, remember, require electrons orbiting nuclei, and nuclei require protons and neutrons bound together, and if proton decay has occurred, as many models of particle physics suggest, then the protons are long gone. The atoms dissolved, one quantum event at a time, over the trillions upon trillions of years of the degenerate era. What remains in the dark era are the particles that are truly stable, the ones at the bottom of the decay chain, the ones with nothing lighter to decay into. Photons. These are particles of light, massless, always traveling at the speed of light. The photons that remain in the dark era are the last photons produced by the last physical processes anywhere in the universe. The Hawking radiation emitted by the final evaporating black holes spread across the cosmos in the eons following the end of the black hole era. These photons are traveling through expanding space, and as space expands, the wavelength of any photon traveling through it stretches. The photon redshifts, becomes longer in wavelength, lower in energy, its frequency drops. The energy of a photon is proportional to its frequency. So as the frequency drops, the photon carries less and less energy. Approaches zero energy asymptotically, the way all limits in physics are approached, forever nearing but never reaching. These photons do not disappear. Photons do not decay into other particles. A photon in vacuum travels until it interacts with something, and in the dark era, there is almost nothing for it to interact with. So, it travels. For timescales that are to the Google year lifespan of the last black hole, as that lifespan is to a single second. It travels, growing fainter, longer, redder, beyond infrared, beyond microwave, beyond radio, into wavelength ranges that have no names, because no instrument has ever been built to detect them, and no instrument ever will be. Wavelengths longer than the observable universe was at the time the photon was emitted. wavelengths that stretch further with every parting eon. Still there, still traveling, a ghost of light in a universe that has forgotten what light was for. Neutrinos. Neutrinos are among the most numerous particles in the universe today. They were produced in extraordinary quantities in the first seconds after the Big Bang, when the universe was dense and hot enough for neutrino-producing reactions to occur at a furious rate. They were produced in stellar cores through the nuclear reactions of the stelliferous era. They were produced in supernovae in quantities so vast that a single supernova releases more energy in neutrinos in a few seconds than the sun will radiate in its entire 10 billion year lifetime. And they barely interact with anything. The phrase barely does not do it justice. Neutrinos interact with ordinary matter only through the weak nuclear force, which, despite its name, is not particularly weak in absolute terms, but is extremely short range. The practical consequence is that a neutrino can pass through a light year of solid lead and have only about a 50% chance of being stopped. They pass through planets as though the planets are not there. They pass through you right now in their billions every second with no effect. You will never feel one. No instrument currently in existence can reliably detect individual neutrinos. The detectors that observe neutrinos do so by waiting inside enormous tanks of purified water or liquid for the vanishingly rare interaction events. In the dark era, the neutrinos from the early universe and from the long-dead stars are still there, incredibly cold, moving much more slowly than in their hot youth, because neutrinos have a tiny but non-zero mass, and the expansion of the universe has cooled them the way it cools everything. They drift. They are essentially non-interactive, part of the background texture of a universe that has nothing else happening. Electrons and positrons. These are stable particles. An electron carries a negative charge and cannot decay into anything lighter because there is nothing lighter that carries electric charge. A positron is its antiparticle, same mass, positive charge, and is equally stable in isolation. In the dark era, the universe contains a sparse and slowly thinning population of electrons and positrons drifting through the void. When an electron and a positron meet, they annihilate, two particles becoming two photons in a flash of energy. More stretched, faint photons added to the universe's dwindling collection. But the rate of these annihilation events in the dark era is extraordinarily slow. The universe is so vast, the particles so cold and sparse, the distances between them so incomprehensible, that the probability of an electron and positron finding each other in any given eon is almost zero. Almost, not quite. Over timescales that dwarf even the Google year lifespan of the last black hole, electrons and positrons do find each other, occasionally, rarely. One annihilation event somewhere in the universe, and then a very long time passes, and another somewhere else, impossibly far away. The universe ticks over these events one by one, spreads across spans of time with no name in any language ever spoken. Each annihilation is a process, a tiny, faint, brief process, two particles becoming two photons, energy changing form one last time. And then those photons join the drifting population of ghost light, stretching endlessly through the expanding dark. Eventually, all the electrons and positrons annihilate or are otherwise gone, and then there are only photons and neutrinos, and the universe expands around them, endlessly, growing colder and larger and emptier with every unit of time. Now, right now, as you lie here, your room is an extraordinary exception to everything the dark era represents. Right now, chemistry is happening in your body, complex organic chemistry, the kind that requires carbon atoms bonded into long chains, requires water as a medium, requires a constant supply of energy, requires temperatures within a narrow range where liquid water is stable, and proteins fold correctly and enzyme reactions proceed at useful rates. This is happening in every cell of your body right now, while you breathe, while your heart beats, While the neurons in your brain fire their electrochemical signals, chemistry requires energy. Energy requires gradients. Gradients require a universe that is not yet at equilibrium. You exist because the universe has not yet finished cooling. That is literally true. The sun is still hot because nuclear reactions are still occurring in its core. Those reactions are still occurring because the sun formed from a gas cloud that collapsed under gravity and compressed its core to the temperatures required for fusion. That collapse happened because the universe after the Big Bang was structured in a specific non-equilibrium way. Matter slightly denser here, slightly less dense there. The seeds of structure planted in the first fractions of a second that eventually grew into galaxies and stars and solar systems and planets and you. You are downstream of the Big Bang's initial non-equilibrium, running on borrowed energy ultimately, borrowed from the initial low entropy state of the universe, mediated through generations of stellar fusion and planetary chemistry and biological evolution. The dark era is when the borrowing is over, when everything that was borrowed has been spent, when the universe has arrived at the equilibrium that it has been approaching for all of its existence. And the extraordinary thing, the thing that keeps coming back no matter how many different angles you approach this story from, is that this arrival is so far away, so incomprehensibly, so vertiginously, so almost comically far away that the distance between now and then is not even a useful thing to try to feel. The universe in the dark era is separated from you tonight by a span of time, compared to which the entire history of everything is as a single breath. The dark era is also not perfectly static. There are theoretical processes that continue on unimaginably long timescales. The Poincaré recurrence theorem, a result from classical statistical mechanics by the French mathematician Henri Poincaré, working in the late 19th century, tells us that in a finite bounded system with finite energy, any particular configuration of the system will, given enough time, recur. Not recur, will recur. The mathematics are unambiguous. Given enough time, the random thermal fluctuations of the particles in a finite system will, by pure chance, occasionally produce configurations that resemble earlier states of the system, even complex states, even states as complex as, say, a galaxy or a star, or pushed to its logical extreme, and physics papers have pushed it there. A human brain spontaneously assembled from quantum fluctuations in the far future for a single moment of confused awareness before dissolving again. These are called Boltzmann brains, after the physicist Ludwig Boltzmann, who contributed enormously to our understanding of thermodynamics and entropy, and whose ideas about statistical mechanics form part of the foundation of modern physics. Boltzmann himself had a tragic life. His ideas were not universally accepted in his lifetime, and he struggled with depression, and he died by suicide in 1906, before the full power of his statistical mechanics framework was recognized. There is something poignant about his name being attached to this particular thought experiment. But the Boltzmann brain is a genuine concept in cosmological physics, not just a metaphor. In a universe running for the kinds of timescales we are discussing, the probability of any given configuration of matter is not zero, and given enough time, even vanishingly small probabilities become certainties. The Poincaré recurrence time for the observable universe is estimated at something like 10 to the 122nd power years. This number is not 10 to the 122nd power. It is 10 raised to the power of 10 to the 122nd power. A tower of exponents that leaves every other number in this story. The Google years of the last black hole, the 10 to the 83rd years of smaller ones, all of it buried in insignificance. Compared to the Poincaré recurrence time, the entire era of black holes is as a single photon compared to the observable universe. And even this number is not the end of time. Time does not end. There is no final moment. There is just the endless expansion of a universe approaching heat death, asymptotically. The ghost photons stretching to infinity, the occasional quantum fluctuations, assembling something brief and incoherent and dissolving it again. The universe, in its vast dark patience, being exactly what it is. It is a kind of peace. I want to suggest that it is a kind of peace. Not the peace of completion in the human sense, not the peace of a task finished or a journey arrived at its destination, the peace of a system at rest, the peace of a thing that has nothing left to do and is no longer doing it. The universe in the dark era is not suffering. It is not struggling. It is not trying and failing. It has simply reached the condition that all its processes were always pointing toward. The entropy is maximized. The gradients are gone. The fire is out. And the darkness is not cold in the way that human cold is cold, shivering, uncomfortable, threatening. The darkness of the dark era is the darkness of a space that has never known warmth and no longer remembers the concept. It is just the temperature of everything, the same temperature everywhere, the background condition of a universe at rest. There is a word for this that physics uses, and the word is equilibrium. Not death, equilibrium. The condition of a system that has reached its most probable state and will remain there, fluctuating slightly but never departing significantly, for as long as time continues, and time continues forever. Somewhere in the dark, a photon from the last Hawking burst of the last black hole is still traveling. Its wavelength is longer now than it has any right to be. Its energy is less than any unit we have ever named, but it is still there, still moving. The last inheritor of all the fire, and the universe expands around it, without hurry, without end. Heat death is a phrase that sounds violent. It sounds like the universe burns, like a final inferno, like everything overheats in some ultimate thermal catastrophe. You can hear the phrase and picture something dramatic, sun swelling, everything consumed, the cosmos going out in a blaze. It is not that. It is, if anything, the opposite of that. Heat death is the name physicists give to thermodynamic equilibrium. Not a violent end, but the quietest possible ending. Not burning, but cooling. Not explosion, but stillness. The universe achieving, over unimaginable timescales, the condition where every point in space is at exactly the same temperature and there are no energy gradients driving any process anywhere. To understand this, it helps to understand entropy properly, not in the loose colloquial sense, where entropy means disorder and things falling apart, but in the precise thermodynamic sense that gives the word its real power. Entropy is, at its core, a measure of the number of microscopic arrangements of a system that are consistent with its observed macroscopic state. Consider a simple example, a gas in a box. If all the gas molecules are concentrated in one corner of the box, there are relatively few arrangements of those molecules consistent with that observation. You need all of them in the corner, which is a specific and constrained configuration. That is low entropy. If the gas is spread evenly throughout the box, there are vastly more possible arrangements of the molecules consistent with that observation. The molecules could be in any number of specific positions throughout the volume, and the distribution would still look uniform. That is high entropy. The reason gases spread out, the reason a drop of ink diffuses through water, the reason a cup of hot coffee cools, is not because some force is pushing them toward disorder. It is because high entropy states vastly outnumber low entropy states, and a system undergoing random thermal motion is overwhelmingly more likely at any given moment to move toward a configuration that has more possible arrangements than one that has fewer. There are simply more high entropy states to end up in. The movement toward high entropy is, at its deepest level, a statistical effect. The second law of thermodynamics, the law that entropy increases or stays the same in an isolated system, is not a law in the sense of a prohibition. It is a statement of overwhelming probability. Low entropy states do not become high entropy states because they are forbidden from remaining low entropy. They become high entropy states because the odds against staying low entropy are extraordinary. And the universe, since the Big Bang, has been the most spectacular demonstration of this principle imaginable. The Big Bang left the universe in a state of extremely low entropy, not because the early universe was simple, it was extraordinarily hot and energetic, but because the matter and energy were distributed in a particular way, a way with relatively few possible microscopic arrangements consistent with it. The seed of structure was planted. And from that seed, driven by gravity and nuclear physics and Ketelis, the universe has been generating and then spending entropy ever since. Stars forming, gravitational collapse reducing entropy locally, but generating far more entropy in the heat and light they emit. Life forming, an extraordinary reduction of entropy in the living organism, paid for by a far larger increase in entropy in the environment through metabolic heat. Everything ordered is paid for by a greater disorganization elsewhere. The universe's entropy budget is always increasing, always. This is the arrow of time, the reason we remember the past and not the future. The reason effects follow causes, the reason you cannot unscramble an egg, the reason a cup that falls and shatters never spontaneously reassembles, the reason you grow older and not younger. All of these are the same thing, the universe moving from lower to higher entropy configurations driven by the overwhelming statistical advantage of the higher entropy states. And heat death is where this process arrives. Heat death is what maximum entropy looks like at the cosmological scale. It is the state where every accessible arrangement of the universe's matter and energy has been accessed, every gradient has been flattened, every hot spot has cooled to match its surroundings, every concentration has diffused. There is no energy left anywhere in a form that can do work. Not because the energy is gone, energy is conserved in physics, it does not disappear, but because work requires a gradient and there are no more gradients. The energy exists, but it is uniformly distributed, useless, unable to drive any process. A river generates power because water flows downhill. Take away the hill and you still have water, just lying flat, unable to power anything. Heat death is a universe where all the hills have been flattened and the water lies still. Not violent, not catastrophic, not even sad really from the universe's perspective, which does not have a perspective. Just the natural completion of a process that has been running since the first instant. Now, there is something worth saying about the relationship between you and entropy, because it is easy to hear about the heat death of the universe and feel a kind of dread. The universe is running down. Everything is becoming less organized. Eventually, all the complexity and structure and life will dissolve into undifferentiated thermal noise. And that sounds, from a human perspective, like a story about loss. But look at it from a different angle. Entropy is not the enemy of life. Entropy is the engine of life. Every metabolic process in every living thing is an entropy-generating process. Your cells do not fight entropy. Your cells harness entropy. They take in low-entropy energy, food, sunlight in the case of plants, and convert it to high-entropy heat. And in the process of doing so, they capture some of the energy difference to do the work of building and maintaining the complex structures of living tissue. Life is not an exception to the second law. Life is the second law, operating with particular elegance and efficiency. You are entropy in full flower. Every breath is an entropy event. Oxygen enters, reacts with glucose in your mitochondria, produces carbon dioxide and water and ATP, the energy currency of the cell. And heat. The heat is disorder, entropy increasing, the universe moving toward equilibrium. The ATP is captured work, temporarily maintained order, purchased with the coin of entropy, and that ATP powers everything your body does. Movement, thought, maintenance of the complex molecular machinery that keeps you alive. You are a machine for turning low entropy food into high entropy heat. And the machine is extraordinary, and the machine runs on the sun. The sun is a low-entropy energy source. It produces photons with short wavelengths, high energy, high information content. Earth absorbs these photons and re-emits an equal amount of energy as long wavelength, low energy, high entropy infrared radiation. The difference, the entropy gradient between incoming and outgoing radiation, is what life runs on. Plants capture some of it through photosynthesis. Animals capture it by eating plants or other animals. The food chain is at its root a chain of entropy gradients, each link powered by the one above it, all of them ultimately powered by the nuclear fusion reactions in the sun's core. The sun is not an exception to the second law either. The sun is generating enormous amounts of entropy. The fusion reactions that power it increase entropy. The light it emits increases entropy. The sun is, like everything else, participating in the universe's relentless drive toward equilibrium. It just happens to be doing so in a way that, as a side effect, powers all of life on Earth. The heat death of the universe is the completion of this process. When the last star has burned its last hydrogen, when the last black hole has evaporated its last virtual particle, when the last electron has found its last positron, when the last photon has stretched to the last possible wavelength, when every gradient has been flattened and every process has ceased. Then the second law is done. Then entropy is maximized. Then the universe is at rest. And here is the deepest comfort in all of this. That rest is so far away, so incomprehensibly, so vertiginously, so absurdly far away that the entire history of the universe, every star, every galaxy, every atom, every life, every civilization, every thought that has ever been thought, is not even a prologue to it. It is less than a prologue. It is the dedication page of a book with more pages than atoms in the observable universe. The heat death is not coming, not for anything, not for you, not for your children or their children's children, or any generation you could imagine, or any generation beyond those. Not for this planet, which has billions of years of continental drift and ocean chemistry and atmosphere and life still ahead of it. Not for the sun, burning through the midpoint of its 10 billion year life. Not for the stars, which collectively have 100 trillion years of fusion ahead. Not for the black holes, which have a Google years of patient existence still to run. The end is a theoretical construct. The now is all there is, and the now is extraordinary. Right now, this moment, as you breathe and your heart beats and your mind drifts towards sleep, you are in a universe that is busy, furiously busy, 200 billion trillion stars burning, galaxies colliding and merging and evolving, gas clouds collapsing into new stars, old stars shedding their outer layers in beautiful expanding shells of gas. Somewhere in the universe, this very second, a star is going supernova. Somewhere, a planet is forming in the disk of gas around a newborn star. Somewhere, on some world we have not found yet, something that we might recognize as life is doing exactly what life does, metabolizing, growing, maintaining its improbable order against the tide of entropy for exactly as long as the energy flows. The universe is alive, in this era, in this moment, and you are part of it, not as an observer, as a participant, as a process, as one of the things the universe does when it has the energy, and the chemistry, and the time. Let that be enough. For tonight, let that be enough. Here is something that astrophysics gives you if you let it. Not just the story, not just the science. Something that lands, if you stay with it, as a genuine feeling, not a metaphor or a consolation or a philosophical position. A feeling, specific, quiet, real. The feeling is this. You are in the right place at the right time, and the evidence for this is written in the structure of the universe itself, not because the universe was designed for you, not because any cosmic purpose has placed you here, but because the physical requirements for your existence, for any existence like yours, for any process of sufficient complexity to experience the universe, are met only in this era, in the stelliferous era, in the era of stars, in the era we are in right now. Think about what it takes to exist. Not to exist as a rock or a cloud of gas, which requires only matter and space and gravity. To exist as a living thing, as a metabolizing, self-maintaining, information processing, experience-having thing. You need chemistry, complex chemistry, the kind that involves carbon atoms bonded into long, flexible chains capable of encoding and processing information. The kind that involves amino acids folding into proteins, nucleotides assembling into DNA, lipids self-organizing into membranes. This chemistry requires atoms heavier than helium, carbon, oxygen, nitrogen, phosphorus, sulfur. And those atoms do not come for free. They are forged in stellar interiors and distributed into the universe by stellar deaths. The first generation of stars, massive, hot, dying in supernovae, seeded the universe with the heavier elements necessary for any of this chemistry. Without at least one generation of stellar death before you, the universe has none of the ingredients for life. You need stars, and you need stars to have lived and died before you. You need energy, a steady, reliable, long-lasting energy source, not a brief one. Life requires geological time to evolve, hundreds of millions of years at minimum, billions of years for anything approaching complexity. So you need a star that will burn steadily for billions of years. Not a massive star, which burns hot and fast and dies in millions of years. A medium star, like the Sun, burning steadily on the main sequence for 10 billion years or so, providing the continuous energy flow that life needs. You need a stable environment. A rocky planet at the right distance from its star for liquid water to exist. Not too hot, not too cold. With enough geological activity to cycle carbon through the atmosphere and regulate the greenhouse effect over geological time. With a magnetic field to deflect the charged particles streaming from the star. With the right mix of elements in the right proportions. With enough time and stability for complex chemistry to get started and be maintained. These requirements are met on Earth. They are met right now. They may be met in other places, on other worlds, around other stars. We do not know yet. But the requirements themselves tell us something important about when, in the universe's history, they can be met. They cannot be met too early. In the first few 100 million years after the Big Bang, before the first generations of massive stars had lived and died, the universe lacked the heavy elements for complex chemistry. There was hydrogen and helium, that was almost it. No carbon for organic molecules. No oxygen for water, no rocky planets, no life. The universe at that point was not yet ready. They cannot be met too late. In the degenerate era, after the last stars have burned out, the energy flow is gone. No more stellar radiation driving photosynthesis or warming planetary surfaces. The chemistry of life requires energy, and the energy requires a star, and the stars are gone. White dwarfs cool toward absolute zero. The universe in the degenerate era is too cold, too dark, too quiet for anything like life as we understand it. The universe at that point has already finished. They are met now, in this era. In the middle period of the stelliferous era, after the first generations of stars have enriched the universe with heavy elements, but before the last stars have burned out. The habitable window. You exist inside the habitable window, and the habitable window, for all its vast extent, 100 trillion years is nothing to sneeze at, is a finite window. It opens, it will close, and we are inside it right now, in the wide middle of it, with the fire still burning in hundreds of billions of stars across hundreds of billions of galaxies. The universe is 100 trillion years old in the stelliferous era, roughly 13.8 billion years old so far. We are about 0.14% of the way through the habitable window, not even 1%, not even a tenth of a percent. We are so early that the remaining time in the habitable window, if you wrote it on a clock face, would be invisible. We would need a clock face the size of a football field, and we would still be pointing at approximately the 12, 0 hours, 0 minutes, approximately 2 seconds past midnight on a 100 trillion year clock. That is where we are. And 2 seconds past midnight on that clock is when all of this, all of civilization, all of science, all of art, all of recorded history, everything you have ever known or read about or imagined has happened in 2 seconds of a 100 trillion year day, which is, among other things, a reason for something like awe, not the awe of being small and insignificant, the awe of being first, the awe of being early, the awe of existing at the opening of a story that will run for longer than imagination can honestly carry, and finding yourself in the first pages while everything is still beginning. The red dwarf stars that are burning right now will still be burning when the sun is a cold black dwarf, and the solar system is a dispersed collection of icy bodies drifting through a dark that has never known light from this particular direction. Those red dwarfs have trillions of years ahead of them. If any of them have planets with the right conditions, and the research on red dwarf habitability is ongoing and complicated, there are questions about flare activity and tidal locking and atmospheric retention. But if any of them have habitable worlds, those worlds have timescales for life to evolve and diversify that make Earth's 4 billion year biological history look like a first draft. Consider what 4 billion years of evolution has produced here. Single cells becoming multicellular organisms, photosynthesis reshaping the atmosphere, complex nervous systems, mobility, sight, language, consciousness, science, the capacity to sit in a dark room and think about the end of the universe. All of that in 4 billion years, from a standing start of chemistry. What does 20 trillion years of evolution produce on a stable world around a stable red dwarf? We do not know. No one knows. The question is real, and the answer is genuinely unknown. And that unknown is one of the most astonishing open spaces in human thought. Not terrifying, astonishing. The universe has not finished producing things. It has barely started. We are in the early chapters of the Stelliferous era, and the Stelliferous era has 100 trillion years to run, and we cannot imagine what the late chapters will contain. We cannot imagine them because we are still in the prologue. And the prologue has produced us, which is something. Think about the physical facts of being alive at this moment. The sunlight that falls on the Earth carries energy produced in the sun's core by nuclear fusion, released as gamma rays in the core, and then bouncing and scattering through the sun's radiative zone for tens of thousands of years before reaching the surface as visible light, and then traveling the 150 million kilometers from the sun to Earth in about 8 minutes, and then being absorbed by the green molecules of chlorophyll in plant leaves, and driving the chemical reactions that build glucose from carbon dioxide and water, and that glucose becoming part of the food chain, and the food chain sustaining you, and you lying in a warm room right now, with every cell of your body running on the converted energy of nuclear fusion reactions happening 150 million kilometers away. You are running on starlight, directly. Every cell in your body is powered, ultimately, by the sun's fusion reactor, not metaphorically. The energy in the ATP in your mitochondria is the sun's energy, converted through multiple chemical steps. The warmth of your body is the sun's warmth, mediated through food and metabolism. You are a node in the network that connects the sun's core to the biosphere, and the sun has 5 billion years of fusion ahead of it. 5 billion more years of sending energy to this planet. 5 billion more years of possibility. That is not running out. That is not nearly over. That is a span of time more than 300 times longer than the entire history of life on Earth so far. Everything that has ever lived on this planet, from the first self-replicating molecules in the ancient ocean to you, tonight has happened in about 4 billion years. And there are 5 billion more years of solar energy coming. The story is not ending. The story has barely begun. Now add the red dwarfs. Add the trillions of years of stellar burning still ahead in the universe. Add the hundreds of billions of other stars in this galaxy alone, most of them with long futures ahead of them. Add the hundreds of billions of other galaxies. The stelliferous era is not in its final act. The stelliferous era is in its opening scenes, and you are here for it. You, lying in this room right now, are part of the most extraordinary moment in cosmic history. Not because of anything you have done or will do, simply because of when you are, because you exist in the window, in the era of stars, in the only chapter of the universe's story when any of this is possible. Being alive right now is not ordinary. It is, cosmically speaking, the rarest and most fortunate position imaginable, because the eras that follow the stelliferous era are not alive. They are not complex. They do not think or feel or wonder or dream. The white dwarfs do not know what they are. The drifting electrons in the dark era do not experience the dark. The stretched photons carry no information about what it felt like to be produced. The heat death is not experienced by anyone, it simply is. The experience of the universe, such as it is concentrated here now, in the era of stars, in the living creatures that the stars make possible. You are not an afterthought of the cosmos. You are, in a genuine physical sense, the cosmos at its most awake. And somehow, the fact that all the eras we have described tonight, the cooling degenerate era, the patient black hole era, the silent dark era, the eternal equilibrium of heat death, somehow the fact that all of that is out there, ahead, far away, impossibly far away, makes right now feel different, not diminished, not threatened, made more vivid by contrast, made more present by the knowing. The fire will go out eventually. But it is burning now, and you are in the light of it. You are still here. The room is still warm. The air is still moving with your breathing. The darkness around you is not the darkness of the dark era. It is the darkness of a single night on a living planet. A darkness that will end in a few hours when the Earth rotates back toward the sun. A darkness that is warm and breathable and full of the sounds of a world that is in the middle of its story. Not near the end. You are still here. Let's come back slowly. We have traveled a very long way tonight. We started here, in this room, in the warmth, in the light, and we followed the story of the universe forward through 100 trillion years of stellar burning, through the slow dimming and death of the last stars, through the cold quiet of the degenerate era with its white dwarfs slowly cooling toward absolute zero, through the long patience of the black hole era stretching to a Google years and beyond, through the final evaporation of the last black hole in its faint burst of Hawking radiation, through the dark era with its ghost photons and drifting electrons, through the concept of heat death and thermodynamic equilibrium and entropy at maximum and the universe at rest. We went to the end of everything, and now we are back. Back in the room, back in the warmth. This room that you are in right now exists at a particular address in the universe's timeline, not near the end, not near any end you can meaningfully worry about, but right at the beginning, in the early hours of the universe's most interesting and most complex and most alive era, in the stelliferous era, in the era that makes rooms like this possible, that makes warm air possible, that makes bodies like yours possible, that makes the wondering possible. If you think about all the places you could exist in the timeline of the universe, all the eons of the degenerate era, all the long silence of the black hole era, all the emptiness of the dark era, and you could only choose one place to exist, you would choose here, you would choose now. Not because here and now are the only options, because here and now are the best option, the only era with warmth, the only era with chemistry, the only era with the energy flow and the molecular complexity and the stable, long-burning stars necessary for anything like you to exist. You are in the best seat in the house. The house is enormous. The show is just beginning. And from where you sit, you have a view of everything that matters. Think about the stars outside. Not the stars you cannot see because the room is dark, but the stars that are out there, whether you see them or not. The sun, having set for this particular night, is below the horizon but still there. Not gone, not extinguished, just facing the other half of the planet for a few hours before the Earth's rotation brings it back. In the meantime, other stars have come out. The ancient light has arrived. Photons that left their source years or decades or centuries or millennia ago, crossing the void, and tonight arriving at the planet, at this hemisphere, at this particular night. Each one of those stars is a nuclear reactor. Hydrogen fusing into helium in the core, releasing energy. That energy working its way outward through the star's interior over thousands of years before finally reaching the surface and being emitted as light. That light traveling at 300,000 kilometers per second through empty space, through the interstellar medium, through the thin outer atmosphere of this planet, and arriving tonight of all nights. On the night you lay down and listened to the story of the universe's end, there is something about that timing that is either coincidental or profound, and the choice between those two interpretations is yours. Physics does not have a strong opinion on it, but you are allowed to find it meaningful. You are allowed to feel, in this moment, that the ancient light and your particular existence and this particular night are part of something that is worth being awake for, even in the half-aware, drifting state that is almost sleep. You are allowed to feel the luck of it, because you are lucky, not in the lottery sense. Lucky in the deep, structural sense that the universe's architecture has produced. After 13.8 billion years of stars and supernovae and chemistry and geology and evolution, a creature capable of lying in a room at night and understanding something about where it is in the story. And that creature is you. And you are doing it right now. Let the body get heavy, not a command, an observation. The body, when it is finished with its work, naturally becomes heavy. The muscles ease, the thoughts slow. The mind begins to let go of the story, just barely, just around the edges, the way you let go of the edge of a pool when you have been holding on and you decide it is all right to float. The end of the universe is out there, impossibly far, beyond the 100 trillion years of stars still to burn, beyond the long cooling of the degenerate era, beyond the patient waiting of the black hole era and the final evaporation and the long dark and the approach toward heat death. All of it out there, real, waiting, with the patience of a thing that does not know it is waiting. And none of it is tonight. Tonight is just tonight. The sun will rise in a few hours. Tomorrow there will be light. The stars you cannot see right now because it is dark in the room are still out there, burning. The red dwarfs with their trillions of years ahead of them. The young hot blue-white stars in their brief spectacular lives. The medium stars like the sun, steady and warm and reliable. All of them burning right now. All of them converting hydrogen into helium and releasing photons and warming whatever orbits them. All of them part of the single most energetic and complex and alive era the universe will ever have. And you are in that era. You are in the warmth. You are in the light, even in the dark. Because the light is not gone. The light is just on the other side of the planet for a few hours. And when the planet rotates back to face it, the light will be there, as it has been every morning for 4.5 billion years, as it will be every morning for 5 billion more. An enormous number of mornings still ahead. Enough for everything, more than enough. The thoughts can slow down now, the story is told. The universe's end is impossibly far away. And right here, right now, in this room, in this moment, the universe is doing the most interesting thing it has ever done or will ever do. It is alive. You are part of that. You are, in some small and quiet way, part of the universe being alive. And the stars outside are burning, and the air in the room is warm, and the end is so far away it cannot reach you. Not tonight, not in any night that will ever matter. Good night.